Hello and welcome. In this video we're going to talk about the energy spectrum. Okay, so this is a topic, this is an aspect or information about a function you can get by looking at its Fourier series. Okay, so let's talk about what this is. The idea here, of course, is that f, you can convert it to an f hat, which is this Fourier series, which is the sum a naught plus n equals 1 to infinity the sum of a n cosine n pi over Lx plus bn sine n pi over Lx, and that's on that interval negative L all the way to L. But the idea here is basically the representation of f is encoded in a naught, an, and bn all together. Actually, let's hold on and I'll just go back and make it a little bit more compact and just say it's encoded in an and bn for n equals 0 up to forever. The idea that basically these are the data for f of x. Okay, you can think of it as, again, a representation. The idea is then, okay, if those values, if these are values, how to understand them? How do we understand them? So one way is to think about it in terms of basically that the idea of that function magnitude. Okay, so let's go to another page. The idea is this: if I have f and I want to look at its magnitude, of course this is going to be a number. How big is f? But another way we can look at it is actually look at the squared magnitude. Okay. All right, and so the squared magnitude, we can write it as the inner product f comma f. We can write it as the integral from negative L to L negative L to L of f of x quantity squared dx. Okay. But now let's see if we can represent this as a Fourier series. If I take f and now represent it by its Fourier series, a naught plus that sum, n equals 1 to infinity, of a n cosine n pi over Lx plus bn sine n pi over Lx, comma, and then I'm going to put the same thing twice now, right there. Okay, now if I go through the process of finding out what that is, we have to compute all of these different products here. So if I go through that process, let's see if I can figure out what I can do here. Now I have to do a lot of cross multiplication, right? I mean, every single thing has to be multiplied by every little other thing there. And that's going to lead to a bunch of smaller inner products. Okay, well, after you do a bunch of work, and you simplify it as best you can, what you do, you end up at this point where you essentially get L over 2 times the sum of an squared plus bn squared, and goes from 0 all the way to infinity. Well, we'll just make the parenthetical that b0 is just equal to 0. Even though b0 doesn't technically exist, we'll just say it's equal to 0. All right. So what we can do is, the idea here is basically the magnitude f squared can be broken into pieces by distinct n values. The idea here is that basically, if I think about it this way, is 2 over L times f in magnitude. This can be written as a0 squared plus a1 squared plus b1 squared plus a2 squared plus b2 squared, and so on and so on up together. So the idea here is that all these different pieces, all of those are basically components of the magnitude squared of f. Okay, so with that put down, what we're going to actually now talk about is those components. Basically, how much of f is in each one of these components. And that is going to be what we now define as the energy spectrum. So we're actually going to give it a name. We'll call it EF. EF, and we're going to index it by n. All right, so it's a function of these input integers, and it's going to be equal to the an squared plus bn squared. Okay. All right. So basically, each one of these is basically each piece of f squared, in effect, up to some constant of proportionality. Okay, you can think of it that way. So it turns out these pieces are very important because, of course, this is basically what we think of as basically the amount of energy and energy in each, or it's the amount of energy. I need to phrase this precisely. It's the amount of energy in F's nth Fourier mode. Another way to think about it is basically it's how much of the nth n pi over L frequency makes up F. That's essentially what it's telling you. So oftentimes this is basically depicted as a graph. So the idea here is that you have E here on one side, and then you have n equals 0, n equals 1, 2, 3, 4, 5, 6, and so on forever. And of course we know that this does have to go to 0 at some point for the Fourier series to converge. So we expect that we're going to have convergence of this Fourier series. So the energy spectrum will decline as you go further and further out on the n axis. And typically it looks something like this. Like that. And the idea here is that basically what you can say is basically that fourth mode, there's more lots of energy here, and of course less here. And of course, and there's of course, and this is a special one that's called the DC energy. Okay, and that's of course the A0 mode. Okay, so the idea here is by looking at the magnitude of the energy in the energy spectrum, you can tell what the frequency content of F is. Basically, it tells you about the frequency content in f of x. That's essentially what the energy spectrum gives you. And I have to say, so in science and engineering, EF of n is very common. You see it a lot they use it a lot to describe signals. It's used a lot in control theory. It's also used in signal processing. It's used a lot in signal processing, and for many people, F is best described by the A and B. Let me undo that. It's best described by this. That it's this term here. Each one of those terms actually represents the most important information that F has. No one really wants to look at the graph of F. They really want to know what the frequency content in the signal is. So for many scientists and engineers, when they're talking about some signal, f of x, if the signal maybe does something like this, right? There's the graph of it as x goes forward. Here's f. No one really cares about that. No one wants to look at it. Maybe it's actually difficult to look at the graph. The graph might be very complex. What they actually preferred is to look at E. And it might have that maybe, if you look at the wavelengths here, you might say, okay, there's some width there, a very common signal width there, and you find out there's a specific frequency that's represented more than others. And that frequency often is related to what you see in the graph. So it's the energy spectrum that's the most important tool, or the most important descriptive tool to represent what F really truly means to the average scientist and engineer in actual professional practice. All right, so let's just do some examples. Okay, so actually I'm going to go and let's revisit two Fourier series from the previous video. Okay, so we had the function f of x, which was equal to 1 minus x. Like that, right? But we actually had two versions of it. We had a cosine series and a sine series. And the cosine series looked like this. Right, the cosine series was a function that looked like that. So this is f even, the even extension. And the sine series looked like this. Like that. Okay, so again, there is the x-axis going out to 1 from 0, and then it went all the way out to negative 1, and here's negative 1 and 1, like that. And there is 0, and that's the x-axis there. Okay, so here are the two, so this is f odd right there, okay? So we had two different Fourier series coming out of it. One was f even hat, and that was represented by the sum. 1/2 plus k equals 1 to infinity of... Actually, let's back up here and not use the k. Now, you remember from the previous video, we're going to use n is equal to 1 up to infinity, and we had the an cosine n pi x, like that, where the an was this. It was equal to 4 over pi times n squared, and that was for n odd, and here was n even. Okay? And then for f odd of x, we had the following. N equals 1 to infinity of, let's see if I can remember, I believe it was 2 pi over n. Okay. Oh, I think I forgot something. There was a squared on that pi in the an as well. All right. So what I want to do here is just, I'll move this up a little bit like that. And now what I'm going to do is look at the power spectra, or the energy spectra for each one of these. So let's look at the energy spectra of this one. We'll put it right there. And actually, I think we should be able to put these on the same graph. I think that would be really nice. I'm going to use red for the even. So let's look at this. The first one is 1, we'll call it 1/2. So we square that, and that gets us, and so that's the 0 mode, so that's going to be 1/4 right there. Okay. And now if I look at the n equals 1 mode, that's going to be 4 over pi squared. So pi is about 3. So that's going to be 4 over 9-ish, 4/9. So it actually goes up a little bit. So 4/9 is definitely goes up a little bit, like there. Oh, I said I was going to do these in red. Let me do those in red, okay? And then if I go to 2, it's going to be 4 over pi squared times 4. Right, so we're going to get down to, now that's about 1/9-ish. Again, I'm just being, oh, actually, I'm sorry, back up here a little bit. That's not quite true, right? Because the even terms are all 0, right? So actually, where is my point? It's going to be right there. Okay, let's try this again. Now, for the n equals 3 point, we're going to have 4 over pi squared times 3 squared, which is 9. So we're going to have a very small number. It's going to be right about there. And then it's 0 again. And then again, it's going to get smaller and smaller and smaller. Like that. So if I look at the graph of the power spectrum, it would kind of do one of these. All right. Now, if I look at the F even, its graph is going to be a little bit, F odd, I'm making a mistake here. These are going to be the Fourier coefficients, so if I take the Bn squared, they become the Fourier coefficients, and that's going to be 4. Oh, you know what? I made a mistake. Everything here has to be squared. So everything gets a little bit smaller. I'm sorry about that. Let me back up and redo those things. Okay. I think it's going to look, the reality is, though, it's going to go like that, and it's going to go rapidly to 0. Still going to do one of these things. It still alternates between 0 and some non-zero number, but it goes like that. Okay, so now when I go to the Bn's, it's going to be 4 over pi squared times So all those have to be squared too, times n squared. Okay, so what's going to happen is, of course, these are going to decay much slower. And they're going to decay much slower, and they're going to go, it might start smaller, but in the long run, it will always be a little higher. So of course the zero mode is 0 there. I should add that part. Like that. Okay. So what's really key here is this decays much slower, and we might want to ask why. And recall, if we look at the odd extension, notice that there's a jump discontinuity. So jump discontinuities do something pretty intense to Fourier series and their power spectra. So jump discontinuities always put lots of high frequency energy into a signal. Okay, so because there's that jump discontinuity, it always puts a lot more high energy into a signal. So the long and the short of the story here is that if you can always try to get a Fourier series without jump discontinuities. If you can find an odd extension or a periodic extension that minimizes the amount of jump discontinuities you have, you're going to have a lower power signal. You're going to get faster convergence. It's not that high frequency isn't useful. It's just typically the convergence is slower, and you're going to have a lot of your power spectrum, or your energy spectrum is going to be big. It'll be bigger as you go out further. Okay. So anyway, I think we're done for this video, and we'll follow up another video with some more detailed examples after this.